Okay, Algebra 2, this is section 2.1. We're starting a new chapter today. So functions and continuity, you're going to find that some of this stuff is stuff that we've already done before, and that is A-okay. So it's going to be a little bit easier for you. This first section right here, onto and one-to-one functions, I no longer talk about this stuff in Algebra 2 because I find that kids don't remember the difference between onto and one-to-one functions anyway, and it's not tested, so we don't talk about it, so cross this little box out. Okay, so that's exciting. Starting out the notes by getting rid of a bunch of junk, all right? So, functions and continuity. When they have like stuff like example 1 and they ask you in your book if it is a function, determine if it is onto, one-to-one, or both, or neither. You're going to get rid of that instruction right there, and all we're going to do is the rest of the instructions. So if you remember from maybe chapter 0 where we talked about functions, every x and y that are out existing together in the world, all of those are considered relations. So you have relations and then you have functions. Relations versus functions. And I'm going to abbreviate functions as FCNS. Okay, functions. I remember talking about functions with you guys, and we talked about how, like, Super Bowl winners, you can have the Patriots, which won the Super Bowl in like the last 3 out of the 5 Super Bowls. Okay, so the Patriots. And then we had like the Eagles won this one. And then somebody else won this one. I'm not really sure. But we had 2019, 18, 17, 16, 15, okay? And we had each one of those winning. Now that is okay that these guys are the Y coordinates and the Patriots are repeating. Y's repeating is okay, but what is illegal is, let's say we had 2019 listed twice, and we had the Patriots winning here, and the Eagles winning here. Okay, that would be bad because this would imply that the Patriots and the Eagles are both winning the 2019 Super Bowl, which cannot happen. You cannot have 2 teams win any one Super Bowl. We're assuming that, you know, they can't tie, etc., things like that, right? So the X's repeating is a bad thing, and the Y's repeating is still fine, right? The Patriots can win multiple times. That's okay, but we can't have two years where 2 different teams are winning in the same year. All right, so what we're going to do is in example 1, we're going to get rid of the last step, and we're going to basically find domain, range, and then we are going to tell whether or not it's a function. So domain and range we're going to list out, and then function versus not a function. Let me go back up. I'm losing my, there we go. All right, so domain. Since these guys are listed as ordered pairs, we're just going to go ahead and list out all the x coordinates. Domains means x's. For the domain, we do our little squiggly brackets and try to put them in order from least to greatest. So I have -6, -5, -3, -1, and 6. Those are already in order. That's fabulous. -6, -5, -3, -1, and 6. In that order, already in order. Great. Range. The range elements are the y coordinates, okay? And those probably are not listed in order. So we have -1, -9, -7, 7, and -9. All right, so I see already that -9 repeats twice, but I don't need to repeat it twice, so I just list it once. -9, I think -7 is the next one. Then I have -1 and +7. So I only have 4 y coordinates because one of them repeats twice. Now, can the y's repeat twice? You betcha. This is still a function because the x's do not repeat. So yes, it is a function. All right, same thing for this one. We're going to list the domain and the range, okay? Domain, list my squiggly brackets. That's supposed to be a squiggly bracket, so sorry. Smallest x is -2. Then I have -1, then +2. Okay, you can already see some problems happening with this because a couple of the x coordinates are repeating. The range values, however, none of those repeat. -2, -1, 0, 1, 2. None of those y coordinates are repeating, so this is not a function because the x's are repeating. So not function. I abbreviate function as FCN, so if you want to do so too, that's perfectly fine. Sorry, I'm not on my normal dot camera. I don't have that at home, so my writing is just a little bit messier than what it would normally be. So All right, vertical line test is another way of determining whether a function is a function or not. So if you can do a vertical line test and it crosses more than one place, he is not a function, versus like this guy where he crosses only one place. For every vertical line that I do, he is okay. So if I think about what part B would look like if I graph kind of just briefly, two of them that repeat, I had the coordinates 2, -2, and 2, +2. Well, 2, -2 would be right here, and 2, +2, ooh, I'm hitting buttons, and 2, +2 would be here, right? And if I do a vertical line, whoa, I can't do a vertical line. If I do a vertical line, he's going to touch at 2 places. So that is bad, which is just re-emphasizing that part B is not a function. So it doesn't pass the vertical line test if I think about the graph of it, because he's touching at more than one place. Okay, now, discrete versus continuous. Discrete versus continuous. People think of continuous as something that goes on forever, which is kind of true, but not only that, we're talking about like each one of these points that live on this line being connected to each other, okay? So discrete is finite and countable. I'm going to put that on here. When something is discrete, it is countable. Okay, I can count how many dots are on that graph. There are 5 of them. That is countable. That is discrete. Versus, think of a line as being a series of a whole bunch of dots all connected together. Okay, so I have a dot that lives on this line that is at like 1.1, and I have a dot that is at 1.11, and I have a dot that's at 1.01 and 1.001, and there is basically like an infinite number of dots that are like decimals within decimals of each other that are living along this line. So basically continuous means that the decimal, I can't write, that the decimal continues. The decimal place of each decimal number continues. Okay, so I'll give you a few examples of discrete and a few examples of continuous. So discrete would be like students in this class. You can count the number of students in this class. All right. Other things that you can count. Now, this is where it gets a little hairy. Some people get confused by this. Students in this class, technically, if we talk about stars in the sky, even though the sky continues on forever and ever and ever, there is an exact number of stars in the sky. We could count it, maybe, if we lived forever and we could count that high, right? But there is a finite number of stars in the sky, assuming we're not talking about falling stars at any period of time, but there is a finite number, a countable number of stars in the sky. So don't think about the sky as being a continuous region. There is a finite number or a countable number of stars in the sky, even though heaven forbid we would actually have to count them. So continuous would be like temperature. Okay, for example, temperature, you can measure 98.6 degrees, or you can measure 98.61 degrees, or 98.611 degrees, or 98.6111 degrees, right? That decimal number could continue on forever and ever and ever. And there is an infinite number of numbers that exist between even just 98.6 and 98.7, right? You could go those ones on forever, or you could change one of those to a 2. So that is a continuous number of numbers that live on a temperature scale. Now, most scales only go to the first decimal, but that doesn't matter. Temperature, you could go out to an infinite number of decimal places, okay? All right, graph the relation, y equals 1/2 x minus 3. This guy, think about what he looks like. What is that an equation of? That's a linear function. Where do you start graphing him? Oh, down at -3. So let's start there. We go down to -3, put a little dot, and then from there, our slope tells us go up 1/2. Whoop, up 1/2, up 1/2, or down 1 to the left 2, down 1 to the left 2, etc. And I'm going to draw my line, and please, please, please let it be straight. It's not terrible. That's not a terrible line. So that's what the line of y equals 1/2 x minus 3 looks like, okay? We want to determine the domain and range, okay? Now, I'm going to put little arrows on this guy because it's going to help us, okay? Now, when you have a function that's not in table format, right? These dots are going on forever, right? The domain, right? Domain, he's touching like 1, and he's touching 2, and he's touching 3, but he's also touching like 1.1 and 1.2 and 1.3, and he's touching 1.11 and 1.12 and 1.213. So we think about this line as being a continuous value because there are an infinite number of dots that live along this line. So whenever you have a linear function or any function that you're graphing, he's always going to be continuous because he's connected and there are an infinite number of dots that live on that line. So he is considered to be continuous. Now the domain is determined by what x's he touches, right? So does he go as far left as -7? Well, yeah, he's down here at -7. What about -4? Yep, he's right here at -4. Or 0, he's down here at 0. Or 3, he's over here at 3. Or 7, what happens if I would go all the way out to 100? He would be all the way up here at 100, right? But he will eventually touch 100 or -100. So what about the domain? What x's left and right does he touch? He will touch every single one of them. So your domain is all reals because he's going to touch everything left and right. Okay, now the range is the last thing that we have to do. Range is talking about the y coordinates. So the y coordinates go up and down, all right? Will he touch -7? Well, yeah, he's down here at -7. If you go over, he's down there at -7. -4, he touches right here at -4 on the y-axis. -3 is where he touches here at 0. Does he touch, I don't know, 2? Well, he eventually, if we go all the way out here, will touch 2. Does he touch 7? If we go all the way out here, he will touch 7. And because there's arrows on him, meaning that he goes forever in both directions, he will continue to go up forever and down forever. And he will touch all of the points up and down. So the range for that guy is going to be all reals as well. He's touching everything going up and everything going down. All of those points will end up eventually being touched. Even 7 up here, which doesn't look like he's going to touch, but 7, if we continue this line on out, he'll touch all the way over here at 7 on the y. So up and down, he's going to touch everything. So let's see, graph the function, determine the domain and range. We did that, all reals for both. Then state whether the equation is 1-to-1 onto both or neither. We're not going to do that. You skip that part, so cross that out. If they ask you that on the homework, don't worry about 1-to-1 onto both or neither. And then state whether it's discrete or continuous. All of the functions should be continuous, okay? Now, just as a little hint, every single linear function looks like a line of some sort. He will continue going on left and right forever and ever and ever, every single one of them, no matter what they look like, as long as they're a line. And he will continue going up and down forever and ever and ever. So the range will be all reals. So when you have a linear function, looks like a straight line, domain and range will always be all reals because he's going to go up forever, down forever, left forever, right forever, eventually. Okay? All right, let's go to the back side. We got a couple more examples on the back side. Evaluate the functions. We are big kids now. So rather than calling this y equals 5x plus minus 1, they will call it f of x, and they do that so that we can plug numbers in for f of x, okay? So x is your independent variable, that's the stuff that you're plugging in, and then y depends upon what x is. So this is called function notation because we have the function of x, okay? Is what f of x is called. So going down here, we have f of 6. They want us to plug 6 in for x. So what that looks like is 2 times 6 squared minus 8 squared. Okay, so when you're doing this, you do not multiply the 2 and the 6 first. In your PEMDAS, parentheses, exponents, blah, 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 you do exponents before multiplication, right? Exponents come before multiplication. So 6 squared is what you're going to do first. That is 36. And then you're going to multiply 2 and 36 together. So 2 times 36 is like 72. And then you subtract 8 from that, and that is 64 is what that should be. So that is what f of 6 is. I plug 6 in, and out spits 64. Okay? Now, f of 2y, even though there's variables attached in there, all they're saying is you're plugging 2y in for x there. Okay? So this is just going to look like 2 times 2y squared minus 8. Okay, so I'm going to do my parentheses and exponents first. I'm going to distribute this exponent through. So here, this is 2 squared and y squared. Okay, so this 2 is just hanging out. 2 squared is 4. Y squared is just y squared. Minus 8. Now, if I take this 2 and I multiply him here, 4y squared is kind of like one piece. 2 times 4y squared is 8y squared. 8y squared minus 8. Now, can I subtract those two 8's from each other? This one doesn't have a y squared, so he cannot. So that is my final answer. 8y squared minus 8. I can't combine anything more than just that. Okay? All right. Next, we're talking about discrete and continuous. Remember that discrete equals countable. Discrete equals countable. Okay? Discrete equals countable. The graph shows the length of the Tour de France in kilometers. Tour de France is like a biking thing. In kilometers each year from 2000 to 2013. So they do a different route every year, and must be that the length of it is different every year. Is this relation discrete or continuous? So is there a finite number of dots on this that I can determine the length or the distance of each race? Yes, so he is discrete. Now, does the graph represent a function or not? Okay, so the easiest way to do this is, let's think about the vertical line test. And if we would draw a vertical line through each one of those points, would he touch more than one point at a time, right? And I am not seeing any of them that would touch more than one point at a time. So yes, I'm going to say yes, function. Yes, function, exclamation point. He passes vertical line test. Okay, now what would this mean if he didn't pass the vertical line test? That would mean that, let's say like on 2004, maybe he has a dot here and a dot there. Can you have two different races going on in 2004? Well, you could, but they never do for the Tour de France. So that's just the way that works. So 2004 does not have two dots associated with him. He only has one dot, as do all of the other years. So he passes the vertical line test. Yes, this is a function. He is a discrete function. Okay, discrete, countable. There are a countable amount of dots on that. Okay, I think of discrete as being a function that has only dots. Continuous would be a graph that has connected lines where you have, you know, decimals involved and that type of thing. Okay, so choose the correct model. A cup of frozen yogurt costs $2 at a yogurt shack, and the cost of X cups of yogurt can be described using the continuous function. Continuous, because this is a linear function, which means a line, and I told you on the front side, lines involve continuous functions because there's an infinite number of points on this line, right? Y is the total cost in dollars, and the graph of that function is shown at the right. So this is this guy. All right, they want us to choose the correct model. All right, the graph of the discrete function for this yogurt scenario is at the right also, which models the cost of buying cups of frozen yogurt. So basically I have two graphs that are showing kind of the same thing, one in which the lines are connected and one in which there's only dots. Okay, now which one of those is more accurate? Well, if we look at this first graph right here, I see a point right here which kind of looks like the point 0.5 comma 1, 0.5 comma 1. And what that would mean is that I have 0.5 cups of yogurt and I'm going to pay $1 for it. Okay? Well, if it's a straight line, this would imply that I could buy like even 0.1 cup of yogurt, or 1.3 cups of yogurt, which would be maybe up there, right? Now, that's not possible. I can't buy, it would be silly to go up to somebody and say, I want to buy 2.7 cups of yogurt. That's silly. So rather than doing that, they put it as a discrete amount, okay, in which you can only buy whole cups of yogurt. So I can buy 1 cup, I can buy 2 cups, I can buy 3 cups, I can buy 4 cups, etc., right? So in this case, it would make more sense to be a discrete function where you don't have decimals in there and can't pay for portions of a cup of yogurt. So which graph is more appropriate for this scenario? Graph B, because he has whole numbers associated with his cups of yogurt. So that's kind of the stuff that we're doing today. I posted your homework assignment on Google Classroom, so make sure you get to working on that. And I'll see you tomorrow.